Welcome to the 56th Theoretical Physics Colloquium by Professor Joe Kapusta, who's a distinguished university teaching professor at the University of Minnesota. He's an associate editor for Physical Review C and the author of the famous book on finite temperature field theory. He received his PhD in 1978 at the University of California, Berkeley. He had several postdoctoral positions, including at Lawrence Berkeley Lab and Los Alamos National Lab. He was NATO NSF postdoctoral fellow and scientific associate in CERN division in theory division at CERN. Then he became an assistant, associate, and full professor at the University of Minnesota. So he was there since 1982. And he was serving as a director of graduate studies since 2010. Over the years, he received very many awards and distinctions. I will not be able to list them all. Let me just mention maybe a couple of them. He had the George Taylor Distinguished Research Award from the University of Minnesota in 1984. He became a fellow of the American Physical Society in the Division of Nuclear Physics and Particles and Fields in 1992. For contributions to finite temperature field theory and its applications to our understanding of the behavior of matter and radiation under extreme physical conditions. In 2003, he became a fellow of the American Association for Advancement in Science. Over the years, he was very active in professional service. He served on numerous national and international advisory boards and committees, review panels, editorial boards, and more. He was an editor of Comments of Nuclear and Particle Physics between 95 and 99. Since 95, he is serving on the editorial board of Heavy Ion Physics, a series of Acta Physica Hungarica. He was on the editorial board of Physical Review C between 95 and 97, and since 1997, he serves as an associate editor of Physical Review C. He served on the National Advisory Committee of the Institute for Nuclear Theory at the University of Washington between 2011 and 2013. He has very wide research interests: nuclear collisions, coagulant plasma, hadronic gas, phase transitions, QCD at high temperature, and many, many other things. He made many contributions, and I probably should say that he was my mentor at the University of Minnesota, and he is an encyclopedia of nuclear and high energy physics. And today he will be talking about a primer on Tsallis statistics for nuclear and particle physics. And with that, I'll give the microphone to Jill.
Okay, thank you very much for the kind introduction. Yes, so I wasn't quite sure what to title this, but it's actually, I would say, more of a lecture or a mini review of this topic rather than original research. There might be maybe one aspect of it that is original, but I'm not even sure about that. So this all started because, as Igor mentioned, I've been handling associate editor, Phys Rev C for a long time, and I have handled many papers that dealt with Tsallis statistics and different points of view on it. And finally, between fall and spring semester, I had a few weeks and I said, okay, I'm going to dig into this. I'm going to get to the bottom of this, just like some of our politicians have said they would. So I did spend the time and actually learned a lot about the topic, and I decided, well, I should write up some notes and share this information with people. So I did give a seminar on this topic earlier this semester, and Igor invited me to give a talk colloquium here. So here we are. So again, this is a little bit more like a lecture than I would say a research seminar. And I hope you enjoy it. So let's see. Why doesn't this scroll down? Oh, there we go. All right. So brief outline, give an introduction to Tsallis statistics. mentioned that it's a non-extensive entropy. There are actually 3 types, 1, 2, and 3, that were developed sequentially over a period of a few years. I'm going to say a few words about all of them, where they come from, then make a connection to the microcanonical ensemble, talk about single particle distributions, Boltzmann equation, which is an interesting aspect of these types of statistics, and then a brief discussion of how they are being applied to high energy collision phenomenology. So it all started in 1988. Constantino Tsallis. People ask me, where did he get this from? And I think the interesting way to phrase it is that he entertained the possibility of ensembles where the entropy is non-extensive, in the sense that if you put 2 systems together, 2 macroscopic systems, the entropy is not the sum of the entropies of the 2 systems, apart from surface effects, for example. This suggested entropy involves 1 extra parameter called Q. And when Q goes to 1, that reduces to the usual Neumann or Boltzmann or Gibbs entropy. Since then, Tsallis statistics has been applied to many areas of both the natural and social sciences. And so I just want to give a very concise introduction to these statistics, what they might mean, and how they are being applied in high energy proton-proton, proton-nucleus, and nucleus-nucleus collisions. So I did not put a citation on this figure. This was from C.Y. Wong and collaborators, 10 or 15 years ago. This just shows experimental data from UA1 all the way up to the LHC. And it shows the distribution of particles, charged particles, as a function of transverse momentum. And if you look at the scales, the transverse momentum goes up to more than 100 GeV. The horizontal scale covers many, many orders of magnitude in differential cross-section. Normally in these collisions, you say, well, if you produce enough particles, you might describe it by a thermal distribution. And that's represented by the black dashed line. That's just an exponential minus the energy divided by some energy scale, which you might interpret as a temperature. The actual solid curves are 3-parameter fits to these collisions. You notice the thermal fit is 2 parameters. There's the effective temperature, T, and there's the normalization, capital A. These are 3-parameter fits with, again, there's an effective temperature, inverse temperature, which is called beta, normalization A, and this extra parameter Q, which comes from the Tsallis statistics. And it's absolutely amazing to have a 3-parameter fit that can cover so many orders of magnitude in cross-section and transverse momentum. And that really piqued the interest of a lot of people. So this is the title and abstract of his first paper, published in 1988. This paper has received 9,000 citations according to Google Scholar. If you focus on those papers that are involving physics, it's approximately 1,500 articles in the archive with Tsallis in the abstract. So awful lot of citations, but you also notice, I think that the majority of them are actually not in the physical sciences. They're in the social sciences or stock market, such things. So what is it? So in statistical mechanics, I taught the graduate course last fall, entropy is defined to be minus the sum over all states, the probability pi of being in the state I, times the logarithm of the probability. So this goes back, and the quantum version is von Neumann, classical ones, Gibbs, probably Boltzmann. I labels the eigenstate to the Hamiltonian. Pi is the probability of being in that state. Now, in that 1988 paper, Tsallis, again, entertained the possibility of ensembles where the entropy has a slightly different form. And it's the form right here. There's a parameter Q. And you look at it and you say, well, where did that come from? Well, first of all, if you take the limit, the Q goes to 1, this reduces to the usual definition of entropy. So there's one extra parameter. How he chose it, I don't really know. He just writes it down. But it leads to some interesting properties, which I tend to go over now. So, first of all, let's suppose that you have two independent systems, A and B, such that the probabilities multiply. So the probability for the system as a whole to be in a state I, system A is in state I, and system B is in state J. So the probability for the joint system is just the product of the two. They're independent, so probabilities multiply. And probabilities are normalized. So if you sum overall probabilities for system A, it has to be 1. Same thing for system B, has to be equal to 1. In other words, the system has to be in some state. Now, when you take this information into account, it's easy to show with Tsallis statistics, the entropy. Tsallis statistics refers to that entropy formula, that the entropy of the combined system is the sum of the entropies of A and B plus a third term, which is 1 minus Q times the product of their entropies. So first of all, this is okay dimensionally because Q is dimensionless and entropy is a number, it's dimensionless. It's not entropy density, it's an actual entropy. But this means that the entropy as defined by Tsallis is not extensive. And that's why Q is referred to as the non-extensivity parameter. Now, this sounds a little bit odd, but you might say, well, maybe there are systems in nature or systems in social systems where the entropies don't add, that there's some, when you put them together, there's some other interaction between them, even though that interaction is not there explicitly. Okay, but this is not enough to define thermodynamics. You also need to talk about the average of an operator. You have to define what you mean by the average of an operator. And you might think, well, that's obvious. But in fact, Tsallis and his collaborators proposed 3 different ways of defining the average of an operator. So the first one that was introduced, type 1, it assumes that the probabilities are normalized in the usual way. Good. But if you want to calculate the average of some operator O, which commutes with the Hamiltonian, otherwise its average would be 0. So the operator O commutes with the Hamiltonian. The average of that operator is the probability of being in that state times the value of that quantity in that state. So the OI without the angular brackets around it remains, take the expectation value of that operator in that state. The eigenstates of the Hamiltonian are E sub I. All that looks good. So, but you say, well, how do you get the probabilities? Okay, so you have to adjust the probabilities by maximizing the entropy at fixed energy. That's what you always do in statistical mechanics, especially quantum statistical mechanics. So you want to maximize the entropy at fixed energy, and you want to make sure that the probabilities are normalized properly. So you introduce Lagrange multipliers, alpha and beta. So you take the entropy, you subtract off a Lagrange multiplier beta times the energy, subtract off Lagrange multiplier alpha times the sum over I of pi, and then you vary the probability, the value of the probability in each state in order to get 0. So that maximizes the entropy, fixed energy, and ensures that the probabilities are properly normalized. So what distribution do you get? you don't get the usual Boltzmann distribution. You get something with a prefactor. The energy dependence E sub k lies here within this square bracket. So it's 1 plus 1 minus q times beta, Lagrange multiplier, times the energy of that state. And then that's divided by 1 plus alpha times 1 minus q and raised to the power 1 over q minus 1. Now,
sorry, where did the q enter on the maximum, on the variational equation before, on the previous slide?
So you have to maximize the entropy. And
Yes.
this is the Tsallis entropy.
Yeah.
So that is this one. That's where that q comes from.
Mm-hmm. Or you substitute that before
Exactly.
you do the variation. Okay.
Exactly. Now, if you use the standard definition of entropy, you just rederive all the standard stuff that's in textbooks.
Thank you.
Now, you look at this expression, and you know, if q goes to 1, it actually does reduce to the proper expression, because you have 1 minus q goes to 0, and 1 over q minus 1, that's 1 divided by something that's going to 0, and this just becomes an exponential. But if you keep q not equal to 1, it could be bigger than 1 or it could be less than 1. And there actually is a limit. There's an upper limit on the allowed energies if q is greater than 1. And there's a lower limit on the allowed energies if q is less than 1. So this is very peculiar, because this system doesn't know what Hamiltonian I have. Hamiltonian would produce, you know, it could produce bound states, negative energies, et cetera, et cetera. So it makes me a little bit uncomfortable. It means that states can never be populated if the energies are outside this allowed range for a given value of q. It means they can never happen. Never happens in your ensemble. What's even also disturbing is that this distribution is not invariant under overall shift in energy. So if you shift the energy by some constant, that changes the distribution. So the definition of the absolute zero of energy is relevant. Now, normally only energy differences matter. In the only case that I'm aware of in the real universe where the absolute zero of energy matters is in gravity. And here we're not talking about gravity. A positive outcome of this definition of averages, which is the conventional one, is that the energy is additive. So if you have two independent systems, the energy of the combined system is the sum of their energies. The energies are additive, but the entropy is not. So that's Tsallis type 1. And that's actually not, you don't see it used in the literature. It might be a couple of papers, but that's not the one that you normally encounter when you read the papers that I have in mind. So then Tsallis and his collaborators also considered a type 2. I said, well, that's, you know, because of those problems, maybe we should define the average of an operator differently. Okay, so they said, okay, again, let's define the probabilities in the normal way. Sum of all the probabilities has to be equal to 1, so the system is in some state. But the averages are not given by pi times oi. The averages are given by pi to the power q times oi. Now, how you justify that, I mean, you can't justify it. It's just a hypothesis, an assumption, a what if. Right? So you go through the same thing. You start with the expression for the entropy, Tsallis entropy, involving the parameter q, and you have Lagrange multipliers to make sure that the probabilities are normalized to 1, and that the average energy is fixed, and you calculate the average energy by multiplying the energy of a given state by p to the power q. And it's exactly the same type of calculation. Now, in this case, you end up with a probability distribution that has a prefactor again, and the energy enters in this square bracket, and it's raised to the power minus 1 over q minus 1, whereas the previous one was 1 over plus q minus 1. Beta, again, is the Lagrange multiplier associated with energy. Now, in this case, things are a little bit different. There's a lower limit on the allowed energies if Q is greater than 1, and there's an upper limit if Q is less than 1, because this quantity in the square brackets cannot be negative. This also has the problem that the distribution is not invariant under an overall shift in energy. As you can see here, if you add a constant to every single energy in the system, state in the system, the probabilities are going to change. This also has a very strange feature that if you take the operator 1, and so the average of the operator 1 should equal 1. So OI is equal to 1. It's 1 for all the states. And you sum over I of PI to the power Q, that in general, that's not equal to 1. Only if Q is equal to 1 is it guaranteed to be equal to 1. So the average value of 1 is not equal to 1 in general. So that was an interesting idea, this type 2, but say physically it doesn't, mathematically, you say, I'm not sure that it really applies to anything that we will encounter in the real world. Now, for independent systems A and B, the energy is not additive, just like the entropy is not additive. So the energy of two independent systems A plus B is the energy of A plus the energy of B plus 1 minus Q, the entropy of system A times the energy of system B, a cross product, plus the symmetric term, entropy of system B times the energy of system A. That looks a little bit odd, especially since the assumption was that the Hamiltonian is the sum of HA and HB, with no interaction between these two systems. So that really goes back to this definition of how you compute the average of an operator. Okay, so if you redefine the entropy from the standard one to this Tsallis type 2, it should not introduce interactions between the systems, but it does. Well, so then we go on to type 3, which is the newest one. And I can look at my notes to see what year that this was published. I think it was 1991, 1992, maybe 1989. It was not in the first paper. So in this case, the type 3 assumes that probabilities are normalized in the usual way, but the averages are computed in yet another unconventional way. In type 2, the average was the sum over I, pi to the power q times OI. But in the type 3, you divide it by the sum over j of pj to the power q. And that looks a little bit better. So at least if you ask for the average of the number 1, you get 1. So if you put in OI is equal to 1 here, you get 1. Now you do the same thing. You maximize the Tsallis entropy, subject to the conditions that the probabilities are normalized and that the energy is fixed. And the probability distribution has a prefactor, and it has another factor involving the energy, square brackets to the power minus 1 over q minus 1. What's different here is that the total energy, or the energy is fixed. The energy of the system appears, and the entropy of the system appears. So the probability for the system to be in state K with energy EK depends upon the total energy of the system, and it depends upon the total entropy of the system. So in order to determine this Lagrange multiplier beta, which some people interpret as 1 over temperature, you have to calculate the average energy of the system and the entropy of the system. And those are numbers that go in here. Now, this does have an advantage in that the distribution is invariant under an overall shift in energy. So if you add the energy, a constant to all the energies, it cancels out here because this involves the energy difference. Second positive quality that this assumption has is that the energies of two independent systems add. So that the energy of two independent systems A and B is actually the sum of the two energies. And again, this goes back to the normalization condition here when computing the average value of an operator. That's what saves you from the, I would say, catastrophe that appears in type 2. So the entropy and the average energy enter explicitly and in a non-trivial way in this distribution. Now it's actually the type 3, the one that most people are using. And it's the type 3 that most people have in their mind when they talk about Tsallis statistics. But be aware that Tsallis himself was involved in all three types.
George, quick question. In the definition of the entropy, you define it through the probabilities, and the probability through the entropy. Is there a consistent solution, or is there a problem sometimes?
Well, not in type 3, but in type 2 and type 1, yes, because that means that a range of energies are disallowed in your ensemble. So you have a Hamiltonian, you calculate all the energies, and with a type 2 Tsallis statistics, some of those states are not allowed in your ensemble. They just would never appear, which to me seems unphysical.
No, it was more clear about 1 and 2, but in terms of 3, entropy is also defined in terms of pK, and pK in terms of entropy. So somehow you need to resolve this algebraic equation somehow.
It's you have to do it self-consistently.
I see.
Yes.
And it's possible always.
Yes, because of the, yeah. So I will give some more examples of this later on. Type 1 and type 2, I'm going to abandon for now. Well, for the rest of the talk, and type 3 is the one I'm going to focus on. Okay, so at least all three types have the correct limit. When Q goes to 1, the probability becomes the Boltzmann one. It's exponential minus beta times the energy of that state. And then there's a normalization factor, which is the partition function, which just normalizes the probabilities. You can also do this with conserved charges, and people have done that, but for simplicity, I'm not going to do that here. For example, you can put in, when maximizing the entropy at fixed energy, you can also maximize it at fixed baryon number, fixed electric charge, fixed strangeness, whatever. You can maximize it with respect to any operator which commutes with the Hamiltonian. And then you have an additional Lagrange multiplier, or a chemical potential, if you want to call it that, in the same way. And then the probabilities are calculated just as I've shown you. But I don't want to go into that. Okay, back in the well, again, I have the year 90s or early 2000s. Zanet and Montemurro were interested in Tsallis statistics, and they noticed something. This Tsallis statistics was being applied in a lot of ways in the social sciences. Distributions, fluctuations in the stock market, all sorts of things. Vortices, eddies, turbulence in rivers. There's a long list of references you can look at. And they noticed something about this way of defining the entropy. They said, let's suppose that you have some variable X. Could be energy, could be anything. And you observe a distribution in this variable X. So the distribution is P as a function of Xi. So you measure the probabilities. They said you can always find a constraint together with the Tsallis entropy, which gives that distribution. So for example, if the quantity that you're looking at, the observable, is some function phi of the Hamiltonian, and we're dealing only with type 3, then the probability in the energy Ek is given by expression that looks very much like the type 3 one, except that Here, instead of having the energy minus the average energy, you have the function phi of the energy minus the average value of that function phi. And this beta sub phi is the Lagrange multiplier. So you observe any distribution, and you can always solve for that function phi of the energy. So this is always possible. And they gave examples of extremely complicated functions. You look at the probability distribution of how many bends there are in a river as a function of the length of the river, the width of the river, whatever. And you can fit it very well, but with very extremely complicated functions. So that's just a side remark. So, yes, so now I had been teaching in the fall semester graduate statistical mechanics, and I said, well, everything should follow from the fundamental hypothesis of equilibrium statistical mechanics. So do any of these distributions follow from that hypothesis? Okay, let's remind ourselves what that hypothesis is. So we're dealing with quantum mechanics. So we have quantum states. And the fundamental hypothesis is that all quantum states with energies lying between E and E plus delta, where generally you consider delta to be small, these are all equally likely. In other words, you cannot measure, generally for a macroscopic system, you can't measure the energy of the system exactly. There's always an uncertainty. And so within that range of energies, there are, in general, a large number of quantum states. And you have no idea which ones are populated, which ones are not. Is one populated more than another? So the hypothesis says that all states are equally populated. So you count the number of states in that energy range with the step functions. So you sum over all states n, making sure that the energy lies of those states lies between E and E plus delta. And omega then is just a number. It's the number of such states, which, it might be 10, more likely a macroscopic system, it's 10 to the 10th or 10 to the 20th. So the probability P of E sub n is 1 over omega, and it's 0 otherwise. So this is the microcanonical ensemble. You specify the energy. There's temperature as a derived quantity. So the standard entropy is logarithm of the number of available states. Okay, and that's extensive. So that if you have two independent systems, the number of states is the number of states in system 1 times the number of states in system 2. It's the product of the two. And the logarithm of the product is the sum of the logs. So it's extensive. Entropy is extensive in normal thermodynamics. So that's essentially where the statement of the logarithm number of available states comes from. Now, if you do the same thing for the Tsallis entropy, and so far there's no type 1, type 2, or type 3, you just put in the probabilities. You have the probability of being in a state is 1 over omega. And so you calculate the entropy, 1 over q minus 1, 1 minus 1 over omega to the power q minus 1. If you take the limit that q goes to 1, this expression goes back to the logarithm. Now, that really emphasizes the difference in the definition of the entropies. Once you have the entropy, you calculate the temperature in the usual way. 1 over the temperature is the derivative of the entropy with respect to the energy. And with the standard definition of entropy, since S is a logarithm, it's 1 over omega d omega dE. But if you use the Tsallis formula for the entropy, and you differentiate the entropy with respect to the energy, it's 1 over omega to the power q times d omega dE. Now, obviously, when q is equal to 1, these two temperatures are the same. But if q is not equal to 1, there's a difference in, well, temperature is calculated in this way. So now what? Now let's consider how you obtain the canonical ensemble from the microcanonical ensemble. So what you do is consider it a closed system. Closed system is divided into two parts, A and B, with total energy E. And you ask for the probability for part A to be in the state N with energy E sub AN. Okay, this is fundamental hypothesis. There's no entropy entering at this point. So that's 1 over the total number of states of the combined system. You have to make sure that the energy lies within that range. And then it's omega B evaluated at E minus E sub AN divided by the total number of states of the combined system. So that's what the probability is. Now, following the usual calculations, you let part A be much, much smaller than part B. So part B essentially acts as a heat bath. Then you do a Taylor series expansion. And you say the entropy of part B is E minus E sub AN, but you subtract and add the average energy of part A. And you do a Taylor series expansion. The fact that this quantity average value of the energy of system A minus the value of the energy in a particular quantum state N is small. And you do a Taylor series expansion in that difference. And so that's given by the entropy of system B evaluated with an energy which is less than the total energy of the system by an amount which is the average energy in system part A plus this derivative times epsilon. And that derivative is 1 over the S to E is 1 over the temperature, which is beta. So beta is really the inverse temperature associated with the major part, B, the heat path. And so now you go back and you exponentiate this formula, and that gives you the probability for system A to have an energy E sub AN, and it's given by a normalization factor times exponential of minus beta E sub AN minus the average value of EA. And normally this the average value of the energy in system A is absorbed into the partition function. So it's just the Boltzmann factor. Now you do the same thing with the Tsallis distribution definition of entropy. Do the same Taylor series expansion. Oops. And what you end up with is that the probability for system A to have energy E sub AN is given by a normalization factor times this quantity in square brackets. And this quantity in square brackets is exactly the Tsallis type 3 distribution. So the Tsallis type 3 distribution is the one which is consistent with the fundamental hypothesis of equilibrium statistical mechanics, not type 1, not type 2. So what have we done? We've assumed that the entropy is given by the Tsallis formula. We ignore the question of how probabilities are computed. We apply the fundamental hypothesis of equilibrium statistical mechanics, and out pops Tsallis type 3. So I would say type 3 is the only one that makes sense if you're willing to assume that form of the entropy. The other two, you can ignore them. Have any questions so far?
There were no posted questions yet.
Okay.
Sorry, just as a quick sort of, I mean, you're arguing very strongly in favor of scenario 3, which you say that you ignore the way probabilities are usually computed. In scenario 2, you ignore things which in quantum mechanics are kind of known to be that we should ignore. Like, I mean, you know, Szilard's engine tells you that if entropy is correlated, and energy is also correlated. 0 point energy says that things are not invariant under energy shifts. I mean, these are things which are natural in quantum mechanics. So why are you saying version 2 is so bad and version 3, which contradicts probability theory, is the right one? This I'm not convinced that, since you asked for testings.
Well, okay. To give it away, I am skeptical that Tsallis' definition of entropy has anything to do with physics. That's my bottom line.
Okay.
But if you are willing to entertain the possibility of Tsallis' definition of entropy, then the type 3 is the one that you should choose, because the other two are definitely not consistent with fundamental hypothesis.
Okay, there is apparently another question from Boris Tomaszek. Do you want to ask it yourself?
Yes, thank you. So maybe it's on this slide, but the question is basically, are two systems in equilibrium, two Tsallis 3 systems in equilibrium if their temperatures are equal?
Well, that's a good question. Let me scroll back up. So for the type 3, the energies are additive, but the entropies are not. So whether they're in equilibrium or not, you know, I am skeptical about making that interpretation.
Yeah.
So what I'm trying to do is go through the math, you know, step by step, and say, okay, this is the assumption, and this is the result, and the consequences. And nevertheless, you know, I showed you at the beginning of the talk that extremely good fit to the experimental data over orders and orders of magnitude using a Tsallis distribution. So, you know, we should continue on, and let's see what comes next. Let's see. That's where we were. All right. So those were quantum states. But now let's talk about single particle distributions, which is what is being applied to high energy particle collisions or nuclear collisions. All right. So let's first consider one fermion degree of freedom. So there are only two states. One state is unoccupied with 0 energy, and the other one has one occupant with energy omega. So that makes it very easy to calculate the probabilities. So here they are. P0, it's empty. P1, it's occupied. And you notice what enters here, the distribution involves, in a non-trivial way, the entropy and the average energy of the system. So you have, from these distributions, you have to calculate the entropy and the average energy before you know the distribution in omega. Okay, now the number operator commutes with a Hamiltonian. So I take the Hamiltonian to be number operator times omega. If you do something else, then that's a totally different type of system. But this is what we normally mean by single particle distributions. So if you calculate its average, according to the type 3, the average is P1 to the power Q divided by P0 to the power Q plus P1 to the power Q. If Q is equal to 1, it's given by P1 divided by P0 plus P1, because P0 plus P1 is equal to 1. It's normalized. So it's just the probability that the system is occupied. So it's not what you would have expected naively. So explicitly, the average number is given by this expression, and the average energy is just omega times the average number. It looks like a Fermi-Dirac distribution, but instead of an exponential, you have something to some general irrational power. But there's a +1 there, and notice that looks like Fermi-Dirac. Written in this way, it's a more compact way of writing it. Remember, energy is the single particle energy. This beta star is not beta itself. The beta is the true 1/temperature. Beta star is related to it, but it's not the same thing. This beta star that enters here is beta divided by 1 plus 1 minus Q times S plus beta E. And so there's a self-consistency condition on these results. Yeah, if you want to calculate entropy in E, you have to do it basically numerically. Now, if you want the quantum limit is when the probability that that state is occupied is very small. So then P1 is much, much less than P0. And in that case, the average number goes to 1 plus Q minus 1 beta star omega to the power minus Q over Q minus 1. In other words, you can neglect this plus 1 in the denominator. And in that limit, beta star just goes over to beta. So in the classical limit, it is 1 plus Q minus 1 omega divided by the true temperature to this power. And so this limit applies when beta times omega is large compared to 1 and Q is greater than 1. So that's for a quantum state. Now, let's suppose that you have an arbitrarily large number of independent states with a set of quantum numbers and momenta labeled by some symbol alpha. Okay, so then the Hamiltonian is the number operator for that state alpha times the energy of that state alpha summed over all the quantum states. And again, you can calculate the probabilities for these independent states. Turns out that they do factorize, and they're written in this way, which is similar to what we had for just a single quantum state. The averages look very similar, and alpha is given by this expression here, beta alpha star. So not only is there a star on the beta, but there's a subscript alpha. So strictly speaking, you cannot interpret this coefficient beta sub alpha star as 1 over the temperature. The true temperature is beta. The true temperature is 1 over beta. What enters here now is the entropy and the average energy for that quantum state. So this coefficient that enters here depends upon which state you're in. It's not, you cannot interpret it as really a 1 over the true temperature of the system. So all of these states are in equilibrium with each other. There is one common temperature, there is one common beta, but the distributions do not readily reflect that dependence on a common beta. That effective temperature depends upon which state you're in. And that is something that Tsallis wrote in his papers, and a lot of authors kind of brush that aside. So how do you get the self-consistency? Okay, well, the total energy is the sum over all states of the energy. Same thing for the number of particles. There is a common temperature, but the beta alpha star is state dependent. Now, if you have a gas of particles, then your alpha gets replaced by a momentum or a wave number k. And the sum over all states goes to 2s plus 1, where s is the spin, a half generally, times the integral over all phase space. So that's what you have to do if you want to do it properly quantum mechanically. Now, what about bosons? Any number of bosons can occupy a given quantum state. And so when you go through the calculation, it means that the probability to have n bosons in a quantum state with energy omega, that means that the energy of that state should be n times omega because you have n bosons in that state. So here's the probability distribution. And you can write down an explicit formula for the partition function, but basically you just get it by normalizing the probabilities. Probabilities are normalized. Now, if you want to know the average number, remember, average number, you're looking at the operator n hat. So the average, the number in a given state is n. So you have to multiply by p sub n to the power q. And then you normalize that by summing over all states m of p sub m to the power q. And in that case, of course, the partition function drops out, and this is the final expression, where again, this beta star is something that's calculated self-consistently. So this is not nearly as simple as the case of fermions. To calculate this expression in closed form is not possible analytically. And Tsallis and his collaborators worked out several methods for evaluating it numerically. In particular, this average number is not written as 1 over something in a square bracket minus 1. You notice that here. Unlike the case for fermions, where did I have it? Slide was it?
Right here.
Yeah, here. So here you see something in square brackets plus 1. For bosons, that is not true. It's not something in square bracket minus 1. If you take the limit q goes to 1, of course, you recover the normal Bose-Einstein distribution. So it's not equal to this. If you now want to extend this to a gas of bosons, you do exactly what we did for the fermions. You have to states alpha, and they're labeled with a wave number or momentum k, and you have to do the sums and the averages in the same way. Now, to be fair to Tsallis, he wrote explicitly in one of his papers that he did not expect so-called Tsallis statistics, or his expression for the entropy, to describe a system of non-interacting particles, in particular a gas. He said, I don't think it describes a gas, but there are unnamed systems to which it might apply. All right, now, what do we do for a gas? What do we do in heavy ion collisions? Well, oftentimes we consider the Boltzmann equation. So let's consider a Boltzmann equation where we have the reaction A plus B goes to C plus D, and the inverse. Yes.
We have a question from Charles. Charles, do you want to ask yourself, or should I read?
Well, I can ask. Hi, Joe.
Yes, right.
If you go back to the Boltzmann case, does the Tsallis statistic admit condensation? It's not clear. It does, but does it?
Where is this one? I do not remember reading anything about condensation. Of course, you're talking about the bosons.
Right, because
Yeah.
analytically, it's not obvious. But,
No, not obvious.
okay.
Good question. Maybe there's a paper to be written there. All right, well, let's look at the Boltzmann equation. So we have the forward-going reaction and the backward-going reaction, and in equilibrium, they balance each other out. So I think everybody listening here is familiar with the Boltzmann equation. So there's some rate W that involves a cross-section or involves the square of a matrix element. So this includes all of the usual quantum statistics. So Pauli suppression for fermions, Bose enhancement for bosons. If you do microscopic physics, just look at quantum mechanics or quantum field theory. It says that the W for the forward-going reaction is related to the W for the reverse reaction by either they're equal or they're related by up to a factor of 2 because of identical particle effects. And there's no question about that. There's no statistics there. You don't have to worry about the entropy. This is just quantum mechanics and quantum field theory. The W depends upon cross sections or the script M's, the matrix elements squared. Those are proportional to energy momentum conserving delta function, direct delta function, PA plus PB minus PC minus PD. So right away you see, well, there might be a problem with Tsallis statistics because energy of two independent systems is, depending on how you do it, it's not, may not be conserved in this way. So what happens to the Boltzmann equation? Well, let's see, perturbation theory, so which is relevant for the Boltzmann equation. The equilibrium distributions are either Bose-Einstein or Fermi-Dirac. In equilibrium, there's no change in the distribution functions. And this leads to the condition that omega, the energy of A plus energy B equals energy of C plus energy of D, energy conservation. If you do the same thing with solid statistics, and let's just choose classical statistics for simplicity, so we don't have to worry about, you know, the +1 for the Fermi distribution or what happens with the bosons, just classical. So there it is, there's a classical distribution. If you require that this distribution be unchanging with time, it requires that energy of A plus energy of B plus Q minus 1 times beta times energy of A times energy of B equals the same combination for C and D. So this is inconsistent with energy conservation and the Dirac delta function constraint, unless Q equals 1, which is conventional statistical mechanics. So this gets even more complicated if you have, say, 3 particles in the initial state and 2 in the final, or vice versa. So what this tells you is that the Tsallis distribution, the F's for Tsallis distribution, cannot be time independent if you believe this Boltzmann equation. With this Boltzmann equation, the Tsallis distributions cannot be time independent. So, well, that problem was addressed too. So it was postulated, and again, use the word entertain and postulate by Lavagno, that the Boltzmann equation should be modified so that the factor FA times FB, classical statistics, so the probability that particle A and particle B collide is a product of those two classically without polyblocking or Bose enhancement. It gets replaced by a function H with a parameter Q. And that function H is FA to the power 1 minus Q plus FB to the power 1 minus Q minus 1, that whole combination raised to the power 1 over 1 minus Q. And that is then consistent with the equilibrium distribution function, which I had shown earlier, the one with classical statistics. If you make this change, then omega A plus omega B equals omega C plus omega D. So everything would seem to be fine, except that I don't know how to interpret such a modified Boltzmann equation. So I don't know what, you ask for the probability the 2 particles collide, it should be the product of the F's, not this strange combination. So physically, I don't know how to interpret it. Mathematically, yes, it's okay with energy conservation. There's some mention that the molecular chaos hypothesis used to derive the original Boltzmann equation is not valid for Tsallis statistics because the system is not extensive. Particles can interact at long range and they're correlated some way or somehow, but there's no real derivation of that. So it's simply a postulate.
Joe, question?
Yes.
Uli?
Yeah, so this Tsallis distribution maximizes the Tsallis entropy, but it evolves under collisions if you describe them in the Boltzmann equation with the standard way of describing collisions from finite temperature field theory. So what happens to the Tsallis entropy as a result of these collisions?
Well,
F changes, and so
yes.
So
yeah,
S must change.
The F would change, and if you put your particles in a box, they should come to equilibrium. And the equilibrium distribution they come to classically is this one. But in order to reach that distribution, equilibrium distribution, and to have energy conservation, you have to modify the Boltzmann equation in this way. So if you go back, the Boltzmann equation, ignore the quantum statistics, there's an FC times FD in one reaction, and there's FA times FB in the other reaction. Those get replaced by this this function.
But the Boltzmann collision term you can derive from quantum field theory from first principles, so to speak.
Yes.
And so how do you derive the modified Boltzmann equation?
You can't. It's postulated.
Thank you for clarifying.
Yes. So aren't you glad that I spent all the time to study this and now can report it without you having to spend 2 or 3 weeks reading,
after so
50
many papers that I have rejected on Tsallis statistics, I'm really happy to hear your talk.
Careful, this is being recorded. All right, so, but if you go back to the beginning, distributions were fit over many, many orders of magnitude by the classical expression. So, for example, you can look at papers by Starr and Phoenix, I mean, way back in early days of Rick, also Alice and CMS at the LHC. They fit their data, and it's a fit. That's all they do. They say we fit it. They fit it to a distribution which is proportional to dn dy, y is the rapidity, and the transverse distribution is mt minus m. Notice that because this, well, they do it because when the transverse momentum is 0, mt minus m goes to 0. But it is also reminiscent of Tsallis type 3 because it's a difference of energy minus average energy. So if you do an additive constant there, it should drop out. Anyway, they fit it with this functional form. So m is the mass of the particle, mt is the transverse mass, m squared of m squared plus pt squared. There's a temperature that enters here, and then instead of a q, they put in some number n. So what does this do? Well, basically, for small transverse momentum, this is basically exponential. It's basically exponential of minus mt over t. But at high transverse momentum, it's no longer well approximated by an exponential. It's approximated by pt to the power minus n. Okay. I'm going to come back to this. How is n related to q? Now, it depends on how you make the identification between n and q. Some people make the identification that n is 1 over q minus 1, in which case it's basically the classical distribution, and then you would associate t with the temperature. Whereas if you make the identification n is q divided by q minus 1, then you would associate with q times t. You would associate q times t with the temperature. All right. Now, when you compare to data at RIC, deuteron plus gold, copper, copper, gold, gold, the LHC, proton, lead, lead, lead. N, this quantity, this number n depends on the colliding systems. It depends on the beam energy, and it depends on the particle species. So if you are going to say Q is some non-extensivity parameter, which tells you something about QCD, reflects something about QCD, but it changes with the beam energy, it changes with the colliding system, it changes even with the particle species. That's, to me, that's highly doubtful. Just like in a thermodynamic system, you talk about a temperature or a chemical potential, those have meaning. You understand what they mean. But if you have a parameter that's changing according to the particle species, I don't know how to interpret that.
Would it be related to the length of the interaction for the given species of particle?
Well, I'll show a table. The results are extremely sensitive to the value of Q. The power of n. Well, okay. The power of n, I'll show on the next slide. I think it is coming. But Q typically ranges between 1.01 and 1.15, which is a very narrow range. But when you take 1 over Q minus 1, that's a very broad range in n. You know, if Q is 1.01, then n is 100. Whereas if it's if Q is 1.15, it's 1 divided by 0.15, which is what, 6, 7. So that's a huge range in N. So saying that there's a relatively narrow range in Q, I think is not very relevant because it corresponds to an extremely wide range in N. And to me, that means that Q is not a fundamental or an intrinsic quantity to be interpreted in terms of new statistics.
Another question from Uli.
Yes, you showed up further below equation 1, you say that this interpolates, and we saw that in the fits, it interpolates between thermal or exponential behavior at low MT to power law at high MT. And this is often interpreted as dominance of collective medium at low MT and dominance of perturbative QCD at high PT. And if you just focus on the high PT region alone, there are pretty good fits. I think I remember using QCD kind of approaches, which leads to power laws. Are you saying that these power law fits don't, you seem to say that this N that you get from these power law fits at high tails, at high PT tails are irregular. They don't satisfy any rules that we know from, that we can justify with underlying fundamental science.
Well, let me go to the next slide. It's this one. Okay, so yes, nice lead into this slide. So as you were saying, collective behavior at low transverse momentum, that's basically exponential. You're gonna have some collective flow velocity as well. High transverse momentum hadrons do exhibit power law behavior because of asymptotic freedom of QCD. Now, if you look at the parton model for scattering of point particles, then N is predicted to be 4. And so then, depending upon how you interpret Q in terms of N, Q is either 1.25 or 4/3. Now, in fact, to say that N should be equal to 4 because of QCD is too simplistic, because there's scale breaking. You're colliding protons or you're colliding nuclei. And so you have parton distribution functions. And so you have to put in realistic parton distributions in the projectile and target. And when you do that, it turns out that Q turns out to be much closer to 1 for hadrons, which means that N is much bigger than 4. For jets, N turns out to be about 4.5 to 5.5, according to Chek and Wang, whose figure I showed at the beginning of the talk. So for jets, they're much more closely reflect the point particle nature of quarks and gluons, whereas hadrons don't very well. And what's being fit in these distributions are hadrons, not jets. So in my view, Tsallis distributions, classical limit is the one that everybody uses. There is an extra parameter, and in my opinion, that parameter just controls the transition from exponential to power law behavior. And it's an efficient parameterization of data because it adds just one more parameter, and it does an amazing job of representing the data, but I don't see that it's fundamental in any way. And sorry about the size of this, but this is taken from a paper by Chen, which I think is still under review at Physics Review C. Maybe on your screen you can blow it up. I'm looking at a rather small one, but for example, on the left, it's gold plus gold collisions at 7.7 GeV, 62, 200, lead plus lead at 2.76. And so these are fits for transverse momenta up to, well, the data go up to about 3 GeV. And these are for different types of particles. And the interesting thing here is that resonance decays are not taken into account, which you produce deltas, you produce rho mesons, and they all decay. And the fact that you can fit the data without taking into account decays of all those resonances is interesting. And so this parameter Q, I think, is just in a way parameterizing this data, but it's missing out on a lot of the fundamental physics. Here are the numbers for lead plus lead collisions, 2.76 and 5.02 TeV. So this one is for pions, kaons, protons, non-strange particles, all charged particles, pions, kaons, protons. Centrality, the average value, this beta is the flow velocity, not the inverse temperature. And if you look at the values of the Qs, they're slightly different for different particles. And you notice how accurately they have to be determined. One, for example, the first one, 1.024 plus minus 0.005. So, and that's because the power that really enters in the distribution is 1 over Q minus 1. So you have to extremely fine tune the value of Q in order to represent the data. And it changes with centrality, it changes with species type. So it's just an efficient parameterization, I think, nothing more than that. So here's my conclusion. I don't want to read it all. I would say if you want to entertain a Tsallis type entropy, the type 3 is the one that is consistent with fundamental hypothesis of statistical mechanics. It is non-extensive. And some people say it's because long-range forces in QCD and something mysterious going on in heavy ion collisions or even proton-proton collisions. I think it's just a way to interpolate between collective flow, collective motion, thermal motion at relatively low transverse momenta and power law behavior at high transverse momentum, which is computed in very different way from perturbative QCD. So that's what I have to say today, and thank you very much for listening.
Well, thank you very much for a very educating lecture. Actually, I enjoyed it truly. So let's go to questions. Masoud Shokri, you're the first.
Hi, I have a very quick question, and that is, what happens to the second law of thermodynamics here with this statistics?
Well, with the type 3, yes, energy is conserved. Entropy is not extensive. So it just means that if your system is going to be described by this type of entropy, it means that you cannot, you put two systems together, and even though they're not in thermal contact with any Hamiltonian, somehow the entropy does say that they are connected in some way. And I just don't, I find that to be unphysical.
Thank you.
Okay. Giorgio Tavera is next. Giorgio?
Yeah, I'm here. Thanks. No, this was a really great talk, which I will forward the YouTube video to many people. I agree 100% that QC, just as a comment, that for QCD phenomenology, I mean, all these fits, my one word is, can you fit KNO scaling? And you probably can't, because this is not a negative binomial distribution, and then everything else follows. However, your main sort of argument, I mean, you come up to version 3, you come up to this version 3 of Tsallis, and then you say, well, it's incompatible with molecular chaos. If you have long-range correlations, you do expect molecular chaos to be broken. Away from equilibrium, Boltzmann entropy and Gibbs entropy are very different. And in my opinion, and it's a controversial topic, Gibbs entropy is superior. Boltzmann entropy is sort of an approximation. And I mean, as I said earlier, I mean, Szilard engine tells you that if you have microscopic quantum correlations, you probably have energy correlations as well, and you have a 0-point energy. So in general, for a system where you have long-range interaction, sort of long-range, not long-range correlations, if you want, I'm not convinced that something like Tsallis entropy doesn't arise as an effective theory. I mean, to me, this averaging procedure of version 3 is the one that looks extremely suspicious, because that's, you know, probability theory. But you see what I mean, right? I mean, but I don't see anything in what you called version 2, which is particularly in physical, and I don't think Boltzmann equation applies in this case.
Well,
Yeah.
remember version 2 restricts the range of energies that are allowed in your ensemble. And that seems a bit odd.
So does quantum mechanics in general. But okay.
Well, you have a Hamiltonian and you calculate the energies, and some of those energies are disallowed, cannot be in your ensemble. And that, you know, people have been studying electromagnetic plasmas for a very long time, but nothing like this, as far as I know, has ever entered. You know, there's Vlasov, Boltzmann equation, long-range forces, and so on, but I don't know that anybody has tried to make a connection. Maybe they've tried and failed between this definition of entropy and such real physical systems.
Okay, are we moving on to the next question then? Okay, Uli.
Yeah. Okay. So the fact that the Tsallis distribution is not a stationary solution of the Boltzmann equation is something that I could live with, because heavy ion collisions or nucleus or proton-proton collisions, they are possibly quite far out of equilibrium, and they are not, and the momentum distribution that you observe doesn't give isn't a snapshot of a stationary state, but it's a snapshot of a transient state on its way to stationarity at some very late point that it never reaches. However, I have always asked myself and people who were using these Tsallis distributions to ask whether there is some other any kind of dynamical model that has the Tsallis distribution as some sort of solution, maybe intermediate solution before it goes eventually to global equilibrium. Are you aware of any work that shows the Tsallis distribution as the output of some dynamical model?
No. I would, if anybody knows of it, I would very much like to know. I have a set of notes that I intend to write up, but I have no idea where to publish them, because this is not original research. Perhaps obtaining Tsallis type 3 from fundamental hypothesis, that's the only thing that might be original. I don't know, but I don't really want to write up a 50 or 100 page review paper. So I don't know where to put this, but I do have the notes, and if anybody has an answer to your question, I would like to know about it, so I can put them in the notes. There's another point. Think about the early universe. Quark-gluon plasma existed in the early universe. Nobody doubts that. So how would Tsallis entropy apply there? The universe was. Are you going to have correlations? These statistical correlations among every particle within the horizon?
Yeah. Well, I don't think we can answer that right now. So let's move on to the next question. Boris Tomasik.
Thank you. So maybe about you, when you want to write this paper, maybe American Journal of Physics would be the kind of journal that would.
I contacted them, and in fact, I found out one of my former students is on the editorial board, and the lead editor, and also Todd Springer, said, well, American Journal of Physics is really meant for undergraduates. So it's any topic associated with undergraduate physics is fine. Graduate students, maybe 10% of their readers are at the graduate student level. And so if solid statistics was being taught in a graduate course on statistical mechanics, yeah, it would be okay. But they said it does not appear to be. So AJP appears to be out.
Okay, but this wasn't my question. But my question was that, I mean, I understand all the drawbacks, but let's entertain the idea. It seems to have something to do with with the long range interactions. But the long range interactions, maybe the question is what is long? So let's say it's long with respect to the size of the system. But then if that is the case, then maybe one should see some dependence of this. I think it's this Q parameter, which would depend on this range. Some dependence of this Q as a function of centrality or as a function of the system size. So universality for the same system size, but dependence on the system size. That's well, it's just an idea to entertain to. Maybe if there is some data on that, and maybe this is just a comment.
I would take it as a comment. I don't know of any data. Q is supposed to be, it's called a non-extensivity parameter, but it is intensive. I'm not sure I've seen any papers where they claim the Q depends upon the volume. Perhaps I have. Yeah.
Okay. Before we go to the next question, there is a comment from Giorgio Terrieri in the chat. He says there are attempts to solve the primordial lithium problem using Tsallis statistics, and he gives a reference to the archive paper.
It's a fit. For reference, it's a fit, but it was, if you take physical significance of it, its correlations between nuclei could help, but probably it has the same validity as the hadron spectra fits.
I think it's also been applied to neutrinos, cosmological neutrino, astrophysical neutrino distributions. But I don't have the reference with me right now.
Okay. I don't see, actually there is another question from the audience, Mubarak Al-Khatani.
Hi. I think you commented on the fits using Tsallis for fits, but there I saw some papers which do some fluid dynamical equations and trying to find the transport coefficients by using Tsallis statistics. Do you have any comments on that?
If like Louis said, if the single particle distributions are out of equilibrium, then maybe you could describe, it's out of equilibrium, you could have almost any distribution which is normalizable. And Tsallis seems to be able to represent the data reasonably well because it basically goes from exponential to power law. And so it might be okay to use that distribution, momentum or energy distribution, when doing the phenomenology. Mm-hmm. But to claim that Q is some fundamental parameter, I think is not correct.
Okay, are you aware of any dynamical model? I think Oli asked this question. I'm not sure where Tsallis distribution function is used as an input, for the distribution function.
And then I might have come across one or two papers where they put the distribution in and attempted to solve a Boltzmann-like equation numerically. Mm-hmm. But I cannot put my finger on it right at the moment.
Okay, but do you have no objection for that?
As long as you don't, no. If it's purely phenomenological, that's fine. For the distribution. Now, to take the entropy as fundamental, I do have,
okay,
a little bit qualms about that.
But in this case, Boltzmann equation itself should be modified. If one assumes the Tsallis distribution.
if you want it to be an equilibrium distribution, so you start out with some arbitrary distribution and you want it to evolve to an equilibrium state, and you
Yes.
want that equilibrium state to be described by the Tsallis energy distribution, then you have to modify the Boltzmann equation.
Okay.
And that modification, I don't know how to interpret it physically. It's just,
But but Boltzmann equation should be modified, right?
yes.
Okay. Thanks.
Okay, I don't see any other questions from the audience. I did have one sort of very simplistic question. You applied this possibility of Tsallis statistics for fermions and bosons. What about anyons in 2 dimensions? Did anybody try?
I don't think so.
Because there might be, I don't know, maybe potentially more physical connection in that case, because it's already not Fermi, Dirac or Bose, Einstein.
Well, let's see. In one of his older papers, Tsallis and his collaborators looked at bosons where you put a finite number of bosons in a given state. Ultimately, they were interested in putting an arbitrary number in any given quantum state. But along the way, numerically, they said, well, let's suppose there's only, you have a limit of 1, a limit of 2, a limit of 10. So that might be, that, I don't know if that's exactly enyon statistics, but
it sounds like,
yeah, so
at least superficial.
So I can send you a reference to that paper.
Okay. Apparently there is another question from Mubarak Al-Khatani.
If I still have time, could I ask one more question?
Go ahead.
Okay, so going back to the Boltzmann equation and that it should be modified. Could you go to that slide, please, and elaborate more on that? Still not sure.
This one?
Yes. Why do we have to modify the Boltzmann distribution, the Boltzmann equation itself?
Because from the microscopic, where is it? Microscopic physics, which is either quantum mechanics or relativistic quantum field theory, you always end up with an energy conserving delta function,
okay,
like this one.
Yes.
And if you put in the Tsallis momentum distribution, we should always make a distinction between Tsallis formula for entropy and the Tsallis energy or momentum distribution. If you put in that distribution, the right-hand side cannot be equal to 0. And so this paper by Livagno, if you send me an email, I can send you the reference to her paper.
Okay.
She said, well, if you really want that as an equilibrium distribution, you have to modify the right-hand side. And she figured out how you had to do it. And I checked it out, and yeah, it does work.
Okay, now if one uses, for example, the relaxation time approximation, does that still, still one needs to modify the Boltzmann equation as well?
Well, with the relaxation time approximation, normally you would start with the Boltzmann equation, and then you do averaging, and you say only one particle with a specific momentum is out of equilibrium, and all the rest are in equilibrium. And then you derive a formula for the relaxation time from the Boltzmann equation. On the other hand, you could just say, well, I don't know where the equilibration time comes from. I just assume that there is one. And then I write df dt is minus f equilibrium divided by tau.
Mm-hmm.
And then the equilibrium distribution is whatever you want it to be. It could be Bose-Einstein, Fermi-Dirac, Boltzmann, could be Tsallis, could be something else. But then the burden is to ask what equation does that equilibrium distribution satisfy? And how do you derive the equilibration time?
Okay.
Okay.
Thank you.
I don't see any other questions. So using this opportunity, I would like to thank Joe for a very educating lecture. It was really entertaining. Thank you very much.